Okay, so I'm going to show you how to derive the control volume formulation from the Irvine and Kirkwood expressions. So we're going to start with the expression for density at a point in space, R. Now this is equal through the Irvine and Kirkwood expressions to the sum over all molecules n, taking the mass of each of those molecules, and we're only counting the expressions using the direct delta function when Ri is exactly equal to R. So mathematically what this is saying is, in order to get the density at a point in space, we sum over all molecules in existence and we include only the molecules located exactly at point R. Now in the original Irvine and Kirkwood expression, this has angular brackets, and we're actually taking an ensemble average. And this essentially then becomes an integral over lots and lots of systems. What we're going to do today instead, because we're actually interested in getting this expression for a single system, is instead to take the control volume formulation. So what we're going to do is we're going to integrate both sides over volume. So the right and left hand side over volume. And what this means is we can get expressions that are valid instantaneously that link the continuum and the molecular system. And this is because the continuum expressions in control volume form are actually weakened form. So you're no longer assuming a continuum valid at every point. All we're doing is expressing averages in a region in space. And this actually turns out to be a much more useful formulation for the molecular system. So how do we get this? Well, essentially we need to evaluate this integral on the right hand side. We can actually move this integral over a volume inside the sum, because the sum of the integral is the same as the integral of the sum, and the masses of the individual molecules are constant during the simulation. So essentially it becomes a problem of actually working out the volume integral of this direct delta function. So to understand this, if we plot this expression on an axis, x and y, we have some point R, and the continuum, it's the continuum point R, density at point R that we're actually interested in. The molecular equivalent is just the direct delta function. So this basically says, if these are xi and yi, we're only going to take expressions when molecule Ri is exactly located at point R, and anything else will be 0. And you can actually think of this in 2 dimensions as basically just the product of 2 direct delta functions, one for x multiplied by 1 for y. So that's just x here and y here, and essentially just the 2 components of that. Okay, so let's look at evaluating this derivative here. So we look at theta I. We're actually going to evaluate this volume integral as basically the double integral in x and y. So you think about the volume integral, it's essentially between 2 limits, let's say x minus and x plus, just the top and bottom limit. We integrate along that line, and then we essentially integrate all of those lines in order to get a volume. So that's integrated between y minus and y plus. So it's just a double integral here. And this essentially defines a volume in a cube in space. So we can use exactly the same process to rewrite this integral as a double integral between y minus y plus, x minus x plus, and we're just using the 2 components of the direct delta function, and y minus y dx dy. Okay, now in order to actually evaluate the integral of a direct delta function, this is well defined. We essentially take the property that the integral of a direct delta function, so x minus xi dx, is a Heaviside function. Now conceptually you can think of this as being, the direct delta function is an infinitely high, infinitely thin impulse. The Heaviside function is a function at 0, until 0, below 0 when it's negative, and then 1 when it's positive. So it's essentially integrating this infinitely high, infinitely thin pulse, and it gives you an impulse function that's switched on at 0. Now this, between infinite limits, we can actually replace by finite limits, b and a. And essentially it just means that we substitute the limits here into the Heaviside expression. So we get b and bxi, like that. Now mathematically, what this is saying, if we plot it as a graph, xi is essentially, this is 0 until we get to b, and then this jumps up and becomes 1. So when this function becomes 1, until we get to a, And then this becomes 1 as well. So it becomes 1 minus 1, and this goes back down to 0 again. So it's a function that's basically equal to 1 between the limits of b and a, and 0 outside of that. And it's called the boxcar function, because it looks like a boxcar. And essentially we're going to use exactly this to integrate this expression here. First in x, so we keep the limits in y, and then what we have in x is basically just the heaviside function of x plus minus xi. So we're just putting in that limit into the top one. And x minus xi. That's just the bottom limit in there. And then this is still multiplied by y minus yi dy. Okay, so it's exactly the same process we've just seen. And then the second integral over y proceeds exactly the same way. So what we end up with is an expression that's the heaviside of x plus minus xi minus heaviside of x minus xi times the exact same expression for y. So we're just doing this integral in y and substituting the top. Okay, so this is essentially what we call the control volume function. And the reason why is because it's a function which basically says this first expression here is saying that between x minus and x plus, this should be equal to 1 in the expression. And if the molecule is located between y plus and y minus, in the y direction, then that's equal to 1. So what we have is an expression in 2 dimensions is only non-zero when the molecule is located between x plus and x minus and y plus and y minus. So it's a function that essentially selects only molecules inside that volume. So a molecule in here is equal to 1 by this function, and a molecule outside is equal to 0. Okay, so this is very, very useful because it allows us actually from a molecular system over the sum to get only the molecules inside that volume, which is then equivalent to this integral of density only within this volume in space. So it's a mathematically equivalent statement to the continuum control volume. The last thing I want to show you is what happens when we take the derivative of this function. So we can take its derivative, say, in x. And in the same way the integral of the Dirac delta function gives you the heaviside, the derivative of the heaviside gives you the Dirac delta function. So our x heaviside functions just become x plus minus xi, x minus xi, and this is times by the heaviside y plus minus yi minus the heaviside of y minus yi. Okay, so we've still got this expression that's 1 in the y direction, but we now have this Dirac delta function that is only non-zero when molecule x component is located either x plus or x minus. So that is basically an expression that's only going to be non-zero when a molecule is actually on that surface. Exactly. So d theta I by dxi is basically an expression that's counting only the surface crossing. So what that means is we have an expression here that basically only counts molecules as they move across the surface. So we give this notation dsi, essentially the equivalent of the continuum surface flux. So between these two pieces we have all the ingredients to actually express the continuum version, so the molecular version of the continuum control volume equations. That is surface fluxes and values inside the volume.